Hey everyone, we're going to move on in chapter 5. Again, we're looking at alcohols and alkyl halides. We've covered so far nomenclature and some of the physical properties of alcohols and alkyl halides. Today, we're going to dive into reactions, and this is going to be our start into reactions in general and looking at reaction mechanisms. So we're also going to introduce kind of in whole the idea of a reaction mechanism. So the main reaction we're going to be looking at is called substitution reactions. And in particular, a type of substitution reaction that involves an alcohol and a hydrogen halide or an acid halide. Notice this is not an alkyl halide that we're starting with. And it's going to make an alkyl halide, so something with a carbon group here and a halide group here, and water. So again, starting with an alcohol, reacting with a hydrogen halide, this is going to be some type of acid. It's going to make an alkyl halide and water. So again, it's a reaction that replaces an OH with a halide, or vice versa. There are reactions of the reverse in which you can take an alkyl halide and make an alcohol. These are called substitution reactions. Now, again, we're going to focus on this particular reaction in which we're starting with an alcohol and making an alkyl halide. Remember, I said you can do the opposite, but we're going to focus on this version. The reason is because alkyl halides are valuable precursors for other functional groups. They represent what we call a synthetic hub, meaning that if we make an alkyl halide, it's easy to then do reactions on this halide, further reactions, and change the molecule further. Remember, in organic chemistry reactions, usually this is a series of reactions to get to our final product. And so making an alkyl halide is valuable to then further other reactions. So again, we're going to study this reaction and look at the reaction mechanism and then just general principles of reactivity. So for this particular reaction, when we look at a substitution reaction between an alcohol and an acid halide, the reactivity of the acid halide, the hydrogen halide, parallels their acidity. So this hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride, which is more reactive than hydrogen fluoride. So remember, when we talked about acidity, we looked at these, and in fact, in your lab, you also looked at these because of their bond lengths. Hydrogen fluoride is the least reactive, while the hydrogen iodide is most reactive. And in general, this holds true for this reaction. Now, the reactivity of the alcohol is going to be dependent on its substitution. And this is why we talked about substitution in the last section. So if you do not remember how to determine the substitution level of an alcohol or of a alkyl halide, go back to 5.1 and review that section. So the substitution pattern is going to be that a tertiary alcohol is more reactive than a secondary alcohol, which is more reactive than a primary alcohol. In fact, primary alcohols are the least reactive. They're almost unreactive in this type of reaction. We're mostly going to be focusing on secondary and then tertiary, which are the most reactive. They're almost too reactive. So again, remember, primary is going to be if there is only one carbon attached to the alcohol. Secondary is going to be if there are two carbons that are attached to the carbon on the alcohol. And then tertiary is going to be three carbons attached to the carbon on the alcohol. Okay, so let's look at an example. Here is a tertiary alcohol. Again, Here's the carbon attached to the OH group, the alcohol, and notice that there are 3 carbons attached to it. So it is a tertiary alcohol. And we're reacting it with hydrogen chloride. This is a medium level reactive acid. And this is 25 degrees Celsius. So if you have any basis of Celsius, 25 degrees Celsius is not too warm. It's a little cooler than room temperature. And so this reaction will happen in a cooler environment. It happens quite quickly and in just a few minutes. It can react with hydrogen chloride and hydrogen bromide in just minutes. Secondary and primary are going to require hydrogen bromide because it's a stronger acid, and it will require elevated temperatures to get the reaction to go. Here's some examples of those reactions. So if you look at this alcohol here, this is cyclohexanol. It is a secondary alcohol because the carbon attached to the OH is attached to 2 other carbons. So this is secondary alcohol. So it requires hydrogen bromide and some heat. Notice this is 80 to 100 degrees Celsius, where 100 degrees Celsius, as a reminder, is where water is going to boil. And we make bromocyclohexane, so the alcohol has been replaced with a bromine, and water. That's always in our product as well for this reaction. Here's 1-heptanol. 1-heptanol is a primary alcohol. Here's the carbon attached to the OH, and it's only attached to 1 other carbon. In fact, if you draw 1-heptanol out, this would be 1, 2, 3, 4, 5, 6, 7. And here's our OH group. So again, 1, 2, 3, 4, 5, 6, 7. The OH is on the 1 position. So here is the carbon directly attached to the OH, and it's only attached to 1 other carbon. So it is a primary alcohol. It requires hydrogen bromide to react and very hot temperatures, 120 degrees Celsius. Now we're going to dive into reaction mechanisms. And again, I'm going to use this substitution reaction of an alcohol to an alkyl halide as our example to explore reaction mechanisms. So again, we're going to be learning about reaction mechanisms, but also learning about this particular substitution reaction. A reaction mechanism consists of a series of steps, and it's going to lead from the reactant to the product. And each elementary step, each position, so this would be an elementary step as we go along from our start to our final, is going to include its own reactants, a transition state, and products. In general, kinetic data, thermodynamic data, and computations, and also experiments are used to support these mechanisms. So we're using all of this data we've collected to get an idea of what's happening. Now, we can't actually see a lot of these transition states. You can't look under a microscope and see them. Although there is one very powerful microscope that will let you see certain states of molecules now. But generally, we can't view a lot of these states. And so we're using multiple types of data to get an idea of what's happening in these mechanisms. Generally, we are interested in how electrons are flowing and the energy progress of the mechanism. So we're going to look at flow of electrons. You're going to use those electron moving arrows. We talked about those where we're showing pushing electrons. And we're going to be looking at energy diagrams to understand how easy it is to go from one transition state to another, how energetically favorable this overall process is.